Hello and welcome to the first homework in Chapter 2 dealing with the traveling salesman problem in Hamilton circuits. So, yeah, let's start at the beginning. I'm sorry, I've had to change the format I'm going to do these videos because of outside constraints and whatever. So problem 1, I'm looking for a Hamilton circuit that starts at vertex x5, which is down here. The first thing I notice about any Hamilton circuit I do is I will have to include both of those edges because this vertex is valence 2. So both of those edges will have to be included. Other than that, I just have to make it all the way around. So I will do this because otherwise I would have created a small circuit here. So that has to be part of it. Other than that, it doesn't really matter what I do. So I'll go from here, there, and then go around here. That is a Hamilton circuit. So if I start at x5, that Hamilton circuit goes x5, I'll go around this way. So that vertex is x6 and then x1, x6, x1, and then from x1 I'm going down to x4, 3, 2, and back to 5. x4, x3, x2, and back to x5. This is a Hamilton circuit starting and ending at x5 because you have to start and end at the same place. In part B, if I can do this, in part B, that's what the graph looks like. Again, we're going to want to start and end at x5. So I'm just going to, when I do this, go inside, I'll go around these pieces there, then I'm going to come back outside and I'm going to go around the outside there. There's no vertices with valence 2, so there's nothing that I have that constraint where I have to think that way. But again, I'm going to go in, go around here, go out, and go around the outside. Notice it does matter if I go in and go around this way, then here I have nowhere to exit. So I do have to go in and go around this way and then go out. So in my vertices, that starts at the x5 because that's where I'm told to start, going into x12 and then around is x11, x10, x9, x8, x7, x6. That completes around the inside, and then I can go back out to x1, which is that top left corner, and then around the outside, x2, x3, x4, x5. Again, Hamilton circuit starting and ending at x5. Part C, this is the graph we're looking at up here. So I am going to start and end at x5 here. I think I am just going to go out here, up, and then make that little cutout here, and then around the outside. So again, I'll go around this piece, into x3, back out around that chunk, and then down around the bottom. So that is part C. If I can do this. Starting at x5, I went out to x4, then x1, x3, x2. So that puts me going out here and doing that piece. Then x7, x6, and then down around the bottom. x9, x8, and back to x5. There we go. Problem 2. For each of the graphs, again, we want to find a Hamilton circuit starting at x5. So, 2A, we're looking at this rectangular grid. On that rectangular grid, starting at x5, I think I'll just go up and go around here, down, oh no, I can't do that. So I'll go up and I'll do this cutout and then go up and go around. So x5, I said I'd go down and then kind of do a zigzag around there and then come up. So down is x9, x10, x6 starts my zigzag, x7, 11, 12, 8. x7, 11, 12, x8. Now I'm done with this zigzag portion. I just have to go up, come across, and go back. So x4, x3, x2, x1, and back to x5. For all of these Hamilton circuits, you could have any Hamilton circuit that goes and touches every vertex, ends up back where it started. So I'm just giving examples of possible solutions. Any solutions would be, yeah. Again, I want to start at x5 here. If you notice, the only thing to be careful of here, because x5 and x7 are connected to every vertex on the bottom, x1 and x3 are only connected to 3 of the vertices on the bottom. So it's not that concerning, but I just have to make sure I don't get stranded at x1 or x3. Or x6 or x8, I think those are the 4 only connected to 3 places. So, but from x5, I could easily like kill this end and then go back up to x1 and kill this end and then back to x5. So, I'll kill that. Wait, what did I do? I went this way and then back to x1 and there. So, I went x5, x8, x7, x6, and that kills these pieces back here. Then I'm going to go back out here and do that. x6, x1, x2, so x6, 1, 2, 3, 4, x3, x4, x5. And again, that's only one possibility. You could have lots of other ones. In part C, to C. Again, Hamilton circuit starting at x5. The first thing I notice about this graph, where am I starting? 1, 2, 3, 4, down here in the bottom right corner. Okay, I notice I have to use these 2 edges because this is valence 2, and I have to use these 2 edges because this is valence 2. Other than that, I can kind of do anything. So from x5, maybe I'll just like go across, up, I'll kill that little chunk there, and then go across, oh wait, no, I don't want to. I'll go across, up, kill this chunk over, is this one not possible? Or maybe I'm just being an idiot. If I kill that, that works. I'm going to go diagonally here, back down, over, kill this piece, over, and back down. Okay, so x5, x9, then back down, x6, x7. So I've gone zigzaggy there, up x10, 8, 1, x10, x8, x1, 10, 8, 1, 2, 3, 4, 5. 2, 3, 4, 5. Good. Question 3. If the edge x2, x3 is erased from each of the graphs in exercise 1, does the resulting graph still have a Hamilton circuit? So, here was the original graph in 1a. So, if I delete x2, x3, I'm deleting that edge completely, and we get this resulting graph, which looks the exact same, except this edge has been removed. And now we're wondering, do we still have a Hamilton circuit? Well, these 2 edges must be included because it's degree 2, or sorry, valence 2. This one also must be included. So then I just have to look for how can I finish the Hamilton circuit. Well, the only vertex not visited yet is x2. So if I just do this, then I've connected stuff and I have x2. That would be a perfectly fine Hamilton circuit. I could name it or just draw this and be perfectly fine. Part B, I've already deleted edge x2, x3, was this edge here. So with that deleted, my other path that I did, going here and around and then back out and around, now fails because I can't do that piece. So I'm going to first look for valence 2 vertices. Those edges must be included. As a result of those edges being included, I might be wrong. Maybe there's a way I could do it going around here, but I think the easiest way is just going to be connect those. So then I'm just looking, how can I connect the rest of this stuff to make a Hamilton circuit? Well, if I just connect, let me see. I can go up and around here down there and connect this down. That's what I'll do. But from there, I'm just kind of looking at it and saying, how can I finish the rest of this stuff? And that's the circuit I come up with. There may be other examples. It wouldn't surprise me. Good. Down here in C, edge x2, x3 was this edge here, which I've deleted already from this graph. So now I'm just looking for Hamilton circuit again. Valence 2, valence 2, and valence 2 are there. That's all my valence 2s. Then I just have to find a way to connect the rest of this stuff. Well, I'll just go in and do that, go up here and across there, and that is a Hamilton circuit. Works just fine. So there's question 3. 4. If the vertex x6 and the edges attached to x6 are removed from the graphs in exercise 1, do the new graphs still have Hamilton circuits? Oh, vertex x6, right. So, how do you do this? Here's the graph from, here was your original graph, if you picture that still being a piece of it. This is vertex 6, and these edges are connected to it. So those 3 pieces will be gone. That resulting graph is this. So now that I have that graph, I just want to know if it still has a Hamilton circuit. So, degree 2, those will have to be part of my Hamilton circuit. I think that's the only degree 2 vertex, so I'll just connect here and go around the outside here. That is one possible Hamilton circuit. In part B, I've already deleted x6 was here, and the edges connecting to it were there, but I've deleted them already. Oh, and there was also an edge here, but I deleted that. So now I have valence 2, those must be included. Valence 2, these must be included. And then from there, I'm just kind of seeing how I can complete this. First thing I think of is if I go up and in there, then I can come down and out here and go around that edge. So I'm going to go up and in there. I'll come down this edge and out there. And then out here. And that is a Hamilton circuit. It works. Down here, I already deleted vertex x6 was here, and there were edges there, and an edge going in here. And I'm wondering if I still have a Hamilton circuit. Valence 1 and valence 1. So immediately I know no Hamilton circuit exists. Because if I have a valence 1 vertex, I could have a Hamilton path, and I could leave here and go around and touch all of these vertices and end there. But there's no way I can like connect these. There's nothing I could do because they're both valence 1. So good. Question 4, part B. I'm looking over here. If you think the graphs in exercise 1 as communications networks, one interpretation might be given to the removal of a vertex and the edges attached, described in part A. Whatever type of communications network this is, that's just saying it's a network connecting different people trying to communicate some sort of information. That information could be a computer network, it could be actually sending a physical object from one place to another, and it could be anything. So, it could be that a building part of the network burned down. I don't know. Kind of a worst case scenario, I guess. Down. It could be that a computer crashed. If you think of the information being relayed around a network, if one computer crashes, you now can't relay through that station. That's the type of idea. If a vertex goes down, you're looking at something like that.